I have Dr. Salvatore Pais and Dr. John Brandenburg here, and they will be discussing the Superforce. So without any further ado, I am going to once again hide my self view, spotlight you gentlemen, and you guys can get into it.
Very good.
Thank you for making this possible.
Yes, thank you for making this. I'm so pleased to be part of this meeting. First, and may I call you Salvador, or what would you like to be called?
Sal is fine. You can call me Sal.
Oh, Sal.
Yeah.
Sal.
Sal.
Okay.
Sal.
Your Superforce thing is brilliant.
No, sir.
Part of its brilliance is that it is so simple, yet it is a small step mentally, but an enormous step conceptually.
Thank you, sir.
Like to paraphrase Neil Armstrong on the moon.
Coming from the originator of gem theory that actually gave us the mass of the Higgs excitation before it was found experimentally, by the way, at the cost of billions of dollars.
I know.
You only gave us so close to 125 GeV, 125 times the mass of the proton. You were the first to put it out there. So I ask you, sir, where's your invitation to Stockholm, and where's the little pin on your lapel? I believe it's gold.
Hey, I'm more interested in the $1 million check at this point. No, I believe my work is slowly being recognized. Paz, we are part of a revolution, and we are breaking out of the regime of the string theorists. You know, the thing I love about your Superforce is that it is simply an inverse force. They had convinced me because of string theory that it was a energy per unit length of a string. And then you said, oh no, that's energy over distance, that's a force.
Yes, sir.
Where did I walk into?
Okay, let's go back to the Superforce equation. So equation
the Superforce equation. Very important.
If you look at it, it really says the Superforce, the C to the fourth power divided by big G.
Yes.
Is equal to the energy gradient at both the Planck scale and the horizon scales. And that's what makes, well, actually it's on the order of magnitude of both the Planck scales and the horizon scales. In other words, it goes from the realm of the very small Planckian, you know, the realm of strings.
Yes.
To the realm of the observable universe. And this is what I believe this equation is so important. Now, Dave Chester said that this particular equation, he thinks he's been able to derive it from the Dirac large number hypothesis. And I'm like,
very good.
And he was trying as a result to sort of say that it's being marginalized because mainstream physics right now does not recognize the importance of Dirac's large number hypothesis. However,
it's just a coincidence, they say. Just a coincidence.
Yes. But this is key. If I am right and this formula holds, then this exonerates Dirac. This means that the Dirac large number hypothesis is no longer coincidence, but it's fact. And
it is.
What is truly, I think, very important from my point of view, the way I look at it, he also asked me why the energy gradient. And I said, wait a second, how would you describe an acting force in a system that you do not know the dynamic state of? It has to be an energy gradient. Hence, a characteristic energy divided by characteristic length. Again, we follow, just like you and I, both you and I follow Occam's razor.
Occam's razor.
And minimalism. Simplicity and minimalism. You can't get anything more simple or minimalistic than energy gradient describing an acting force.
Simple dimensional analysis leads you
to the truth.
But yes, getting back to your Superforce.
Yes, sir.
Now you believe you have connected this, and I I am not a quantum field theorist, even though it is a useful limit for me to dabble in, down to the Planck scale.
Yes.
That's a very good boundary condition that I use. But yes, I am not, by training or even outlook, a quantum field theorist. So you'll have to forgive me. And I'm trying to learn, by the way. I'm trying to learn. So if you could walk me through your Schrödinger.
Yes, yes, absolutely. If you can permit me to put on my reading glasses, I'm getting to a certain age where I no longer have what, how should I say, the sight that I once had. Oh my goodness. Well, I used to be able, I still remember being able to read. I was absolutely, I used to read things that were at least maybe 100 feet away. I used to be able to read something on the size of about 2 inches. That's not bad. 100 feet.
That's not bad.
Those were the days. Now I can hardly read this. That's how bad it is. Anyway, so Sir Penrose, which I believe Lord Penrose, so
Lord Penrose,
King Charles III, Your Majesty, if you ever watch this, please make the man a lord.
Make him a lord. Elevate him to the peerage.
Yes, yes, he deserves it, among all others. Now, so Penrose writes, as a simple example, using the particular case of a quantum Hamiltonian, we can now write the Schrödinger equation for a single particle of mass m, moving in an external field whose energy contribution is V equal V of x, y, z, of course. But again, the particle of mass m is moving in an external field whose energy contribution is V equal V sub x. And this is very important because David Chester challenged me on this. And here's the response to his challenge. I thought it through. And if you can listen to this, please do. So if you remember the Schrödinger equation, it basically it has an imaginary part equaling to what you'd call a momentum part, plus its rest energy of the background field. Let me take this off. It makes me look like my, anyway. So this V sub x. Now, Dave Chester said that I'm actually introducing the Planck scale in such a way as to give me the superforce. So in other words, I'm putting the superforce in to get out the superforce. That's what Dave Chester.
Who said this,
I remember you stating something of that same nature in your APS conference. I remember, I think you may have been on APEC, but anyway, we'll discuss this further. Let's focus on the Schrödinger equation.
Yes.
Maybe this is a sort of, anyway, so Schrödinger equation.
Continue.
And the whole idea, again, simple mathematics.
Simple mathematics.
There is something called conditional replacement technique that I came up with in a paper that I call him Dr. Paul Murad, so I'm not gonna stop. So Dr. Murad read that paper. It took me 4 years to publish it. It's called Conditional Possibility of Spacecraft Propulsion under Superluminal Speeds, or rather at superluminal speeds. And in it, I describe a technique, a one-to-one correspondence technique called conditional replacement technique. I'm not using that in this paper. What I'm using in this paper is something I call, again, think of the terms in an equation. They are there because they're important. So every one of those terms has relevance to that equation. Yes. So as far as the physics is concerned, think of physics. Don't think of mathematics now. Think of physics. From a physical mathematics perspective, whereby physics drives the mathematics. it actually says, when you have an equation, say A equal B plus C, it says that from a physics perspective, from an order of importance, A is of the same order of importance as B, is of the same order of importance as C. Otherwise, they would not be there.
No.
There would not be terms of this equation. So from a physical perspective, they are of equal importance. So what I did, if you look at, do you remember the imaginary term? It's on the order of I, H bar, d psi dt, the partial of the wave function. It's a time derivative of the wave function.
Yes.
Okay. Now, you remember what V sub x is, what Lord Penrose says V sub x should be. It is basically the rest energy of a field for which the particle of mass m is moving. So if you take, okay, so since all terms are of equal importance, you take that imaginary term, the I h bar d psi dt, okay? And you take that last term, the V sub x, and you equal them. Equal importance. Just simple, very rudimentary, but again, looking towards physics. Look carefully what it says. Forget about the imaginary part, because remember, remember Euler's formula, the whole idea of e to the I pi plus 1.
Yes, it is a rotation.
Yes, exactly.
It's a twist.
That the imaginary part, the e to the I theta equal cosine theta plus I sine theta, everything is equally important. Just because it has the I in it doesn't mean you disregard the sinusoidal function. Agreed? See,
absolutely.
Again, physics driving the mathematics. This is the beauty of it. Okay, so from that first term, the I h bar d psi dt, and the same order as Vx, if you look at that, V sub x is really an energy. It's the background energy, the rest energy of the field for which the particle of mass m is traveling. Now, according to Penrose, Lord Penrose.
Yes.
Okay, King Charles, please. Okay, okay, so if you look closely at that h, right? H divided by dt, it's really what? What's 1 divided by t like? A frequency. H bar. See? Do you want? It's the Planck-Einstein equation for what?
Oh, so you can get the Planck, length from the Schrödinger equation.
Yes, sir. Thank you.
I've never seen that done.
Thank you. This is how easy this thing is. No, eventually I'll show. There's a little more mathematics involved where you can show the when you equate terms, I believe 1 and 2. So you equate the one that has the mass of the particle in it, with the first term, with the I h bar d psi dt. When you equate that, you get the de Broglie wavelength. When you put it out, trust me.
Okay, I will.
When you put the reference length as the lambda of that moving particle, again, particle wave duality. That's the whole idea.
Particle wave.
You get the de Broglie wavelength on the order of h bar divided by mv, which is the momentum of your particle.
Yes.
Right?
Right.
The Bohr's equation. Okay, and now this is the pièce de résistance, as the French say. The pièce de résistance is this. When you take term 2 with term 3, and this is unbelievable. When you take term 2 with term 3 and do a little manipulation, and you put for your characteristic length.
The term 3 is the potential.
Yes. Remember, it's the rest energy of the background field for which the particle of mass m is moving. So when you take term 2, which is the one that has the particle mass in it, and this V sub x, and you put for your characteristic length gh bar divided by c cubed, square root of, right? Because that's Planck length. You get what? You get for your energy gradient, when you do the energy gradient.
The Superforce.
You get c to the 4th divided by big G. So David
very good.
David Chester cannot say that I put in the super force and got out the super force. What I put in is exactly what I said. The super force resides at the Planck scale. At the Planck scale is what? Planck length. So therefore, your characteristic length must be GH
and that means
bar
you have a potential, and if you divide it by the Planck length, then you
get the super force. How?
Fabulous.
Why is the super force in the Schrödinger equation? And it's an easy manipulation to show if it's in the Schrödinger equation, as you well know, because it's a linear system, it's a linear equation.
Linear equation.
The same thing applies to the Dirac, because Dirac is just Schrödinger plus special relativity.
Yes, it is.
Thank you.
Hey, Sal,
anyway,
about the Superforce, or I always called that the Planck Force.
Yes, it is the Planck Force.
It is. And all these Planck scale objects, Planck length, Planck time, Planck force, Planck charge, even like the fine structure constant, I look at it's E squared over the Planck charge squared.
Right.
It's same, it's all in there. I just see these as a baseline based on our own man-made constants that we created to equate to the units we defined. And it's like, to me, it's like you have a deep bucket with a flat bottom base, and up here on the top, the wind's making the top ripple, and that's what we have to work with. And down here at the bottom of the deep bucket, you've got a baseline that you can't change.
Yep.
Agreed. Good observation. Now
none of that really has any, let me finish. None of that really has any effect on anything we can do other than reference it as a common baseline. I did a paper about this back in like 2004, where I took Hal Puthoff's PV model, which is an analog of curved spacetime.
Yes.
And I looked at it from what would it look like on a flat tangent plane. So what would it look like if you took the PV model and wrote it and revised the mathematics to describe the same thing without a variable speed of light? And what you get is a variable density function instead of a variable impedance function, instead of a variable refractive index, instead of it changing the speed of light, 1 over mu naught E naught square root, it affects mu naught over E naught, the impedance function. But there is a complete, mapping, one-to-one mapping of all the equations over from one to the other. And that mapping depends on dividing by different multiples of Planck scale objects. So you would map length from the curved spacetime model to the flat spacetime model by dividing length squared by the Planck length squared. And then using the density function, the impedance function, would map what that would be in terms of a refractive index in a polarizable vacuum model. And so it really is nothing more than a baseline for mapping one frame of reference to another. And
I disagree. And let me say why. Let me disagree with you. All right. Todd, we find this Planck force in the general relativity equations of Albert Einstein.
Yeah,
which
it's
they
force
shouldn't
for the
be
Planck
there.
force.
The Planck force, which is a Planckian quantum, actually, if you think of it, it's the only Planckian variable, or rather the only Planckian parameter that does not have H bar in it, does not have the quantum of action in it.
It does. It just canceled out twice.
Which means that it can operate on the classical realm as well as the quantum realm. Why? Because it talks to a super density. Remember, a super density, if you think of the Planck force, think of it like the force is on the order of a pressure times an area. So what we're talking about is like the super density times c squared times L squared P, where LP is the Planck force. That super density comes out to be on the order of c to the fifth divided by g squared h bar.
Mhm.
So it's on the order of 10 to the 96 kilograms per meter cube. 10 to the 96 kilogram per meter cube. Well, I'm arguing there's an analogy between our mechanism of supernovas based on core bounds and how the superforce gives rise to a superbang at the super density.
Okay.
This may be a whole different perspective on inflation. It may actually give us, okay, my question is to the illustrious mainstream physicists. I ask, what is a Planckian parameter doing in general relativity? Because you can actually
can I answer that?
No, let me finish and then you can answer any, I promise. But this I must say, because it gives a certain conclusion. It reaches a certain conclusion, in my opinion, a new perspective on all physics. Now, it's not new physics. It's a new perspective on all physics. And this is it. If you look at Einstein's G sub mu nu on the order of 1 divided by Planck force or superforce times T sub mu nu, it actually says space-time curvatures on the order of 1 divided by the superforce times the whole thing times T sub mu nu. Now, these are same rank tensors. They have to be. Otherwise, right? That's a scalar parameter. Put it on the other side. What does it say? It says the superforce acting as a linear operator on the local spatial-temporal geometric structure gives rise to energy density, hence matter. Do you remember a certain, and this is what I question.
You're saying.
No, listen, just one more thing, and I promise you can talk for the rest of the thing, but this is important because I'm putting it out. Tim might want to cut this out because maybe mainstream physicists listening to this will say, my God, this is total crackpot. But what if 3D printing out of space-time fabric is feasible based on the action of the superforce? If we can nudge the superforce, we can actually, maybe this is how quote unquote ET tech works. And this is what I'm really weirded out by. The way Bob Lazar describes the sports model, saying it's as if it was grown out of space-time itself. Well, this freaking equation talks to that. What if this guy is not full of shit?
Well, doesn't that goes to entanglement and quantum teleportation and things like that?
Oh, that
also,
too, right? Of course. But it also goes to something he said, which is very strange. Anyway, yeah.
Well, to get to back to your question, and that comes out because I mean, and John would probably verify this too in GEM, that if you look at what is the gravitational impedance equation, you're going to get G over C squared. And in terms of Einstein's equation, when you want to convert from energy density and go to curvature, which is what everything has to be in to do geometry, the unit of conversion from one to the other is 1 over the force. And just like I was saying, the most natural baseline to use, which really has nothing to do with quantum mechanics, it has to do with how we classically defined our units of measure, would be to reference energy density to the Planck force. So energy density over the force gives you square meters, which is curvature. And that's just the natural way things would go. It's classical. It's not quantum. It's classical. But even classically, our human defined units of measure, the way we defined a meter from the king's thumb to his nose, is referenced in all of those constants because it's referenced in energy, and Planck's constant converts from energy to frequency. And and force, and Newton's constant converts from energy to force, and they're defined on units of measure that we created as human beings. And John likes to work in CGS, and I like to work in SI. His CGS numbers drive me nuts. You know,
I worked in
I have to
SI.
convert everything when I read his
your
paper.
epsilon zeros.
But this is just.
I don't like dragging the factor of pi or 4 pi.
I agree, but it was drummed into me so long talking with so many other people.
I know.
If I don't do it that way, it just confuses everybody else.
I can testify that is true.
Yeah. But anyway, so what I want to say, Sal, is that I don't believe in space-time. I think that's a misinterpretation. General relativity does not, Einstein's equation does not say what people think it says. What it says is that given the right-hand side, T mu nu, this is everything we know about matter and energy and quantum mechanics and the strong force and the weak force and all the other forces all fall under T mu nu. And given instruments made of matter, clocks and rulers made of matter, under the conditions set forth by T mu nu for the volume of space-time we're talking about and the matter in it, it describes what we will measure on the left-hand side using rulers and clocks made of stuff from the right-hand side. And space-time is no more or less than what we measure with rulers and clocks and instruments made of matter and energy. It's not a fabric. It's not a thing. These are the things. T mu nu. These are the things. Everything else on the left-hand side is the stage. And we measure what we want. What we measure is due to the quantum interactions between the things, not the stage.
Interesting.
So a ruler contracts in a gravitational field because the probabilities, the probability amplitudes for all that matter interfere with each other and cause damping. And when you add just a tiny amount of damping to a quantum harmonic oscillator, its wavelength contracts and its frequency slows down. So all you have to do is consider in our normal quantum mechanics that if you simply consider the damping that takes place because of non-coherent interference or incoherent interference between matter, and what that does to the atoms, which are just spherical harmonics, they're going to contract, they're going to slow down, and it explains gravity without ever invoking the need for a space-time manifold. The manifold is something that we measure using matter and energy.
I like where you're going. I was gonna add some.
This is why it's so hard. This is why it's so hard to mate general relativity with quantum mechanics, because general relativity is not needed. It's an interpretation. It's a misinterpretation.
Can I say something?
Please. And Jeremiah.
Okay, let me say this, and then Jeremiah can take the next thing. I believe, it is my strong belief that Einstein's general relativity is not only correct, but is actually extremely close to the final solution. I think he was extremely close to it. The reason that anyway, I'm not going to go into the reason why he could not come up with a unified field theory. Only a great like Einstein would go there. So I am just a mere apprentice of the man. What I'm trying to say is that the Superforce equation would not hold correct if there was not a link between the realm of the very small and the realm of the very large, the observable universe. The Superforce equaling the energy gradient at both the Planck scale and the observable universe scale known as the horizon scale That cannot be a coincidence.
No, it's
And that
not.
comes right out of GR. So if GR is
GR2.
wrong, everything else is wrong, including what? The freaking Dirac equation, Schrödinger's equation that has been proved over. And why? Because we find, I look toward the first segment of this where I explain to Dr. Brandenburg exactly how I find the superforce in the Schrödinger equation. How can the Schrödinger equation show the superforce is there if the superforce was not important? And the superforce also is important. You cannot tell me that Einstein knew that was the Planck force. I do not. Einstein refused to believe in quantum mechanics. As a matter of fact, he was very much against it. The Bohr-Einstein debates are some of the most fascinating dialogues in the history of science. It's absolute amazement. I mean, the idea of quantum entanglement, wow. And I tell you, Bohr almost lost the one on based on Einstein-Rosen bridge, the idea of ER equally. But anyway, Bohr almost lost that one. And then he remembered that Einstein wrote this little something. He actually used Einstein's own writings against him. That's how Einstein lost the final debate. Can you imagine having your own work used against you? Todd, I would have freaking died. I would have been so pissed. I would have knocked Bohr through the wall. I don't care, you know what the.
I was on Usenet in the 1990s. I got a skin as thick as a turtle.
Very good.
That's right.
That's good. It's good to have that skin.
No, but between you and I, hey, Doc, would you agree with me? When people get physical, you know they love the physics.
Yep.
That's true.
That's for sure. Hey, well, so that relationship you mentioned, did you know that if you take Friedman Walker Robinson equation and the reciprocal interpretation of that equation, and you take the Hubble constant, Hubble constant equates to, say I had a meter stick in my hand. Okay, the Hubble constant equates to this meter stick contracting 6.8 nanometers every century.
Oh, wow.
So if the size of this meter stick depended on the quantum environment here, causing it to have this proper length, and here energy is running down and decreasing such that my meter stick is contracting 6.8 nanometers every century. And I look back in time as I look out into space. And if everything were doing this from a common Big Bang or a common starting point, then what I would see is everything will appear to be accelerating away from me and redshifting because my ruler is getting shorter relative to those wavelengths. And so that would connect the cosmic horizon to the smallest scale here on Earth.
Jeremiah needs to speak.
Yes, please.
Jeremiah, go ahead, sir.
Okay, so in one model here, Todd, you're presenting us with a stress energy momentum density equivalent in space-time that allows us to calculate out the, well, curvature equivalence, or in the more correct terms, the actual energy momentum in any given volume of space and its gradient, if one should apply, particularly in mass. The issue with it is, well, the mechanism of action there for curvature does not actually reveal the underlying substrate that causes the curvature to take place in the first place. So
yeah, it does. I said it was. Go ahead.
Well, it's field force interaction based on measurements, but they don't actually reveal the underlying substrate of why there is said distance over X space and time. Hence, if it's beyond the probability scale, we have to acknowledge the particle pair and the tremendous number of particle pairs in each unit of Planck distance. because
That's
without
one
that,
field.
we don't actually have a explanation for why the mass energy density or the angular momentum or the other various factors of that localized space has the properties that it does have. So we have to acknowledge that it has some properties that are very much like mass.
You're making an assumption that it has a property without interacting with anything else.
Well, we have various factors that are within already our very well recognized mathematics, like the local K of our space-time, the refractive index. We have our epsilon and mu. We have our
Yeah.
That's
G.
it. You hit on it.
No,
Why-
no,
why
but
would you
you're
use-
you're misinterpreting what I'm saying based on your understanding.
Cosmological constant,
And
the gravitational constant, these
let me
things have to
back
be
up a
defined by
second.
something. There's got to be something there to define them. And that's what I'm saying.
Yes,
It's like,
there
You
is.
got it,
There
Jeremiah. You got
is,
it.
and it should
You
all
got
be
it.
included in T mu nu. Everything, all stuff is in T mu nu. The vacuum energy is in T mu nu. It's
What?
part of it.
No, that's a cosmological constant that he brings in.
It can be
on the
added
other
in there.
side
T
with-
mu nu can have a
with the
constant.
Riemann curvature and the Ritchie tensor. He also adds
T mu nu can have a constant
he also
added
adds
to
the
it.
lambda.
T mu nu
It's
can
on
have
the
a
left-hand
constant added
side.
to it. It doesn't have
That's
to
so-called
be a separate
quantum energy.
entity.
Vacuum energy.
I'm saying that if you take away T mu nu, there is nothing. There's no particles popping in and out of
I disagree.
existence. There is
I
just a stage.
No. The quantum
It
vacuum is a
has
material
no
medium.
matter.
to be.
If there is no
Otherwise,
matter,
mu
there is no
zero and
thing.
epsilon
If
zero
there is
would
no
not exist.
thing, there's nothing.
No. I totally disagree with that. The
You
quantum
have to have a
vacuum-
field. Sal, you have to have a
Look at-
field. The particles come from the field. The first entity you put in the vacuum
Look at
is a
Frank
field.
Wilczek's work. Look at Frank Wilczek's work and the idea of materiality of a vacuum.
I don't like Frank Wilczek's work, to be honest.
Well,
I've read it. I don't agree with them. I'm more likely to agree with I can never remember his name. I'll think of it. Never mind.
I think the man is a genius and deserves another Nobel Prize. How's that? And I mean that.
It makes no sense to me, to be honest.
It makes total sense to me. As a matter of fact, the idea that they would take his axion and pervert it, and I'm totally against it. I think they should find the original axion, his axion, not this one Kathy Fries is looking at. She was on Brian Keating talking about it. Anyway. Yeah.
My point is that I look at it is that you have to start with a field. You don't start, the empty vacuum has no shape. It has no particles. You have to add a field before you have any pair creation. Before you have any particles, you have to add a field. And as soon as you add a field, it's not empty anymore. It's not space. It's not empty space. It's space filled with a field. You can't measure time until you have a particle that's moving to clock it.
What do you think time is, Todd? What do you think
time is? What you measure with a clock.
No.
Clock, I'll measure
physical time. What's physical time? Do you think,
what
for
you measure with a
example,
clock.
physical time can have multiple dimensions like space could have multiple?
Nonsense.
No?
It's nonsense.
What?
Physical time is what you measure with a clock. That's all it is.
Eric
no
Weinstein
fourth dimension.
greatly.
There's no fourth dimension. Now is all that exists.
Todd, time is the expansion of the universe, basically.
Yeah.
That's really the best clock for time that we have.
Yeah. I don't believe
it's
in
an
the clock
accelerated
universe. The past
expansion.
still exists and the
It's an
future already
accelerated
exists
expansion,
and
so
everything
it's
is predetermined.
quality
I
of
don't buy
time
that.
is an energetic informational field.
Yeah.
Since we're dealing with an accelerated
That's a
expansion
clock.
of the universe. Yes, but it's a collective field. So what is it made out of? The things
Particles.
that are. I'm saying our understanding of physical time is inadequate. We should research
Our
it further.
understanding of physical time in general is very confused. Even among physicists in the mainstream. What one physicist says is time and another physicist calls time
Agreed.
completely different.
Carlo Rovelli thinks very different than Julian Barbour thinks very different than Lee Smolin. I do agree with
I
that.
take it down to the basics. Time is what I can measure with a clock.
Mm.
That's my observation.
Yeah, but that's
any
your
clock I
engineer's
want.
look to it. You have to step back and look at the fundamental of it. What is physical time?
I don't believe there is a physical time because I can't measure it.
You can measure heartbeats.
I think it has a lot to do with
That's a
entropy,
good
the state of
clock.
entropy, phase transition.
I have a great ticker right here.
You know, so you're saying basically, until you measure it, there is no time.
Exactly.
Oh,
Okay, I
Time is
understand
what you
that.
can measure.
I grasp that.
so
Well,
to you,
and
time is
just
an
to-
illusion.
If you
if I
can't
could
measure it, it don't
To me,
exist.
it's
It has
physical.
no effect.
It's a physical entity. Lee Smolin agrees with that. Time is real. Julian Barbour and Carlo Rovelli believe in time is more of an illusion, an illusory entity. I believe Lee Smolin is correct. Time is very real. Physical time can not only be altered, it can be manipulated. But that's me. Eric Weinstein also believed in multiple dimensions of time, just like we have multiple spatial dimensions brought forth by string theory. One should not put down string theory because you disagree with the lack of experimental verification, period.
I like
Okay,
string.
because it looks to me like
It
Maldacena
leads to
came
conformal
upon
gravity, and that's what
experiment that was
I have is
performed in
conformal
1968.
gravity. So
Anyway, yeah, I mean, we agree to disagree. This is the
so
beauty of physics.
if I let me, so John mentioned time being related to the expansion of the universe. One thing I have wondered, I'm going to showcase how dumb I am right now, but
Nah, you're not dumb.
if the universe
You're not
is
dumb.
what the
Damn,
universe
you're
is
organizing this conference.
Then
well,
I'm a certified idiot.
the universe is one. The universe is like unity, right? The universe is one. Is the universe expanding, or is maybe the universe staying the same size and everything in it is becoming more detailed? Maybe losing energy, shrinking, not shrinking. Shrinking is a bad word, but dissipating.
I believe
becoming more entropic.
Every unit is contracting.
I know I'm splitting hairs, but it's one of those paradigm changing. This occurred to me a while ago.
Oh no, and paradigms, concepts are extremely important. That's why
John,
the Superforce
mathematics says it could be either way, Tim, because if you look at the equation one way, the universe is expanding and everything else is staying the same size. If you look at the equation the other way, the universe is the same size, but we're observing it from a contracting galaxy, from a contracting.
Yeah, well, so maybe that contraction is the actual function of entropy.
Can't tell the difference. There's no measurement you can make to tell the difference.
I know. That's I'm.
Have you seen Roger Penrose's idea? Instead of inflation, what could birth the universe? Have you seen his cosmological theory?
Yeah, but I don't understand the connection between an absolutely everything's evaporated and there's nothing left, and then suddenly you've got a singularity to start a new one. I don't buy that. In Roger Penrose's cyclic universe,
Have you read
he ends up with nothing, and then there's a new singularity. Why?
Have you read Abai Ashtekar? He talked, okay, in this book, if you ever have a chance, get Conversations on Quantum Gravity by it's a compilation of conversations with greats like Nima, Juan Maldacena, Abai Ashtekar, right? By Jacques Armas. Read carefully the part, not only Juan Maldacena, but read Nima as well, but read Abai Ashtekar especially. The part on the quantum bounds. It is freaking pure genius. I think this is how it was done. And it talks directly to the Superforce. You see, the quantum bounds has an analogy to supernovas. And let me explain. Can I explain why I'm saying this? Okay, and tell me if the physical mechanism makes sense to you. Please do, because this is important to me. As you well know, in a supernova, once the fuel runs out, it starts imploding. It comes to, say, on the order of 10 to the minus 15 meters. So we're talking about 1 femtometer. That's the realm of the strong nuclear force. It resides at 10 to the minus 15 meters. So we're talking about the strong nuclear force is there. Now, The densities we're talking about is on the order of 10 to the 14 grams per centimeter cube. So again, not exactly small, but not exactly Planckian either. So because of the strong nuclear force, there is a core bounce. It basically tells it tells the implosion, stop, you shall not go any further. This thing rebounds and it explodes, hence the supernova. Well, I'm saying there's an analogous mechanism with a superforce at the super density on the order of 10 to the 96 kilogram per meter cube. This contraction, it undergoes what Ashtekar calls quantum bounds. I call it an Ashtekar bounds. The whole idea is that the superforce at 10 to the minus 35 meters at the Planck scale tells the mechanism, you shall not go further. And again, this thing undergoes a quantum bounds, hence the formation of a new era, a new epoch of the possibly a new universe. But why not a super intelligence? Do you realize that most of our universe, you know, the work of Anthony Peratt, 99.999% of our universe is made out of plasma. Remember the Bussard ramjet, the whole idea of, you know, yes, you need huge scoops and all that, because again, the energy density is extremely low. It's on the order of 10 to the minus 9. It's not, you know, we talk about 120 order of magnitude difference between quantum field theory and general relativity as far as the vacuum energy density is concerned. Yes, it's true. But if it is plasma, check this out. Just hear me out. This sounds a little bit weird. But what if plasma under certain conditions has a capability of sentience, consciousness being activated on a macro scale? So basically the universe becoming a super intelligence, not an artificial super intelligence, but a natural super
That's
intelligence.
beyond my pay grade, man.
I'm just saying the possibility may exist. That's all. I'm just putting it out there.
Yeah.
So what I'm saying, I'm talking about something I call the triarchy of creation. Superforce based on the super density, which again is Planckian, because the superforce bridges the realms, and so superforce leading to super bang, leading to super intelligence. I call it the triarchy of creation. It's just an idea. It's out there.
No, I was listening to Brian Greene and Sabine Hassenfelder telling me that the universe is deterministic, and I'm like, that doesn't even.
Well, in a way, if the super intelligence exists and it controls everything, yes, it is. It is deterministic. If such a super intelligence would, basically, this super intelligence would have the ability.
I binge watched Loki last night. You should watch it because that's what the end was.
No, that's
Loki is really good.
Huh?
If we're talking about time, people should watch.
Loki!
He finally got what he wanted.
The Norse god, was he brother to Thor and all that? Odin?
Oh, yes.
No, he was the child of Odin with some giantess or something,
right? Yeah.
It goes off on a tangent and it goes into this. Basically, he does something that he's not supposed to do, and the time police arrest him, for creating a new timeline, and they're about to erase him, and then they use him to find another Loki who was off on another tangent, and it just becomes this whole time traveling bonanza.
Let me bring it back. Mark, let me bring it back to super intelligence, because I think this is important. Let me bring about another analogy I've always wondered about, and let me throw it out there. The human brain supposedly contains on the order of 100 billion neurons, synapses and such. Our so-called observable universe has 100 billion galaxies, each with 100 billion stars in it. So again, this number, if you believe in the Dirac large number hypothesis, it's possible to make the analogy, what if This super intelligence is really a Boltzmann brain. You're acquainted with the Boltzmann brain. You know, Sean Carroll talks about it all the time, you know, as a popping. What I'm saying is, what if this super intelligence exists? What if this is what we're talking about? What if it reinvents itself with a quantum bound just to auto-experiment on new possibilities? I know this is wild speculation, but I'm saying what if? And it's all based on the state of plasma. What if plasma, under certain conditions, can become sentient?
Well, there are several authors.
Oh, as a working plasma physicist, I can tell you the plasma is sentient already.
Really? How would you
It has a mind
characterize
of its own, and you have to convince it to do what you want, but you can't try and force it.
Interesting. Very interesting.
There have
So
been
you
several
have to
authors that have
rather than
hypothesized that. So,
force
and
Okay.
I don't remember the name of it. Pete Gerritsen told me a book that he was really excited about.
Oh,
that apparently-
Gerritsen, interesting guy.
Yeah, and he just finished a big book, and the idea in that book was, what if plasma filaments in
Is
galaxies?
it bigger than this? Is it bigger than this? Is it bigger than Roger Penrose's epic, in my opinion? The road to reality, 1,050 pages of absolute genius. This man should be lauded by King Charles III of England.
No, the road to reality is long.
If you ever
It's
listen
long.
to
It's
this
a long
podcast,
road.
if you ever listen to this podcast, please, Lord, yeah, absolutely, peerage all the way. This is a beautiful book. This is this is a must-have, along with a Superfluid Universe by Kirsten Huang and Carver Mead's Collective Electrodynamics. Unbelievable. Those 3 books, baby. I don't know what I have with the number 3. It is what it is. Anyway. Yeah. Okay, I'm done.
Yeah, well, no, thank you. I mean, yeah, in terms of recording, so I would love to be able to put this up at APEC. You know, I'll edit. I will edit heavily. We'll probably end up with about an hour of usable footage, but that's okay.
Please make sure that whatever we say about mainstream physics is laudatory. We want them to engage with us, bro.
Yes.
We don't want them.
My comment to Brian Greene.
Definitely. No, we want them to start being more malleable, more, you know, like take us seriously. Right?
Why
now,
don't
I?
So why don't I stop? Let me stop recording now. I'm going to stop recording, and let me thank you guys both. And
yeah, I want to thank you.
Stop recording now.
Thank you for having us. Wonderful as usual. You have the absolute best interviews, bro. Listen, anybody that likes John Brandenburg and Salvatore Pais, please subscribe.
Sal, come on. Yo, Sal, you're the guy who invented the Superforce.
Nah, man, you invented gym theory. I mean, you gave life to the pointing vector. Everybody had forgotten about how important the pointing vector was. Anyway.
That's how I know there's a God, by the way, because he's a punster.
Okay.
The pointing vector points in the direction of the momentum flow, even though they're spelled different.
On that note, let me thank you both guys, and Todd as well, and everyone, Jeremy Riss and Jeremiah Pop and Mark Sokol. Thank you guys.
Live long and prosper.